Hello and welcome to today's video. Today we're going to talk about basis and dimension of a vector space. And the idea here is to use the notion of linear independence that we have just defined to derive a minimum set that generates a given vector space. And such a set will then be called a basis of a vector space. So this section is called basis and dimension. And the idea today is to find a set that generates a vector space and has no redundancies. So it's minimum in the sense that it's irredundant. Let's define that straight away. Of course, the idea here is to use linear independence as a measure of irredundancy. We already know that if a set of vectors is linearly independent, then removing any vector from that set changes its span. So a linearly independent set will always be what we want in terms of irredundancy. So as a definition, of basis and also of dimension, as always, we'll start with a vector space. So let V be a vector space. And then a subset of that vector space will be called a basis if two conditions are satisfied. The first one, it needs to actually generate the vector space. So the span of a set is the vector space. And the second one, it needs to be irredundant, meaning it needs to be linearly independent. A set, let's call it B, subset of V, is called a basis of V if two conditions hold. The first one, the span of B is equal to V. And second condition, B is linearly independent. In other words, a basis is a linearly independent generator of a vector space. Now, the second notion we will define is that of the dimension. And here we'll just say if we have a basis of a vector space, then we can measure how many elements are contained in this basis. And this measure gives us an idea about the richness of the vector space, how large a vector space is. As you notice, most vector spaces that we are dealing with contain infinitely many vectors. But still, their size is different in a way. So in R2, consider a line and consider the whole R2. Those all contain infinitely many vectors, but we'd still like to differentiate that somehow. And that is what the dimension does. A line is generated by one single vector. The whole space R2 is generated by two linearly independent vectors. So the dimension is different and gives us an idea of how large that vector space actually is. So if B is a basis for a vector space V, then its cardinality is called the dimension of V. And that dimension is denoted by dim of V. Of course, for that definition to make sense, we'll have to make sure that all bases of a given vector space have the same cardinality. One can prove that, and actually we have kind of proved that already for vector spaces that are linear subspaces of R to the n. One can extend that proof to general vector spaces, but we're not going to bother with these technicalities in this lecture here. I'd like to add one more thing. By convention, you know the set, the empty set, generates the vector space that consists just of the vector 0. And in this way, the empty set is considered a basis of that trivial vector space, and its definition, its dimension is therefore 0. So by convention, the empty set is considered a basis of the vector space that consists just of the vector 0, and thus the dimension of that vector space is the cardinality of an empty set, and that is, of course, 0. So that just one point is a 0-dimensional vector space. And let's just add what I said about the cardinality of different bases as a quick remark. One can show that all bases of a given vector space have the same cardinality. In fact, for linear subspaces of R to the n, that follows from our discussion of systems of linear equations. Now that means in particular that definition does actually make sense because it's independent of the bases that you actually choose. So the definition of dimension does not depend on the choice of basis. And finally, let's apply that idea of dimension right away. we'll reformulate one theorem that we know that we have about systems of linear equations that characterizes the solution space. We know already that the solution space of a system of linear equations is a linear subspace of R to the n, if we have n variables in that system. Now we can even characterize the dimension of that space. The dimension is characterized by the number of free variables, so n minus the rank of the left-hand side. Basically, we know that fact already, but we can now express it in the language of dimensions of a vector space. So let A, right-hand side 0, be a homogeneous system of linear equations in n variables. Then the solution space of that system, A0, is a linear subspace of R to the n of dimension n minus the rank of A. Of course, there is a similar characterization for the solution spaces of inhomogeneous systems as well, because as you know, they can basically be characterized in the same way. It's just a translation that makes that space different. But we'll introduce the necessary notions a little later on, and then we'll extend that theorem to inhomogeneous spaces as well. So this concludes our discussion of basis and dimension. In one of the upcoming videos, we'll see a few examples of how to actually compute a basis and find out the dimension of a given space before we go further in our investigations of vector spaces and the associated ideas. I'll see you then.